The story of who we are and where we came from is always at the root of every tradition of knowledge and discourse about the past. In this lecture, we'll be talking about the evidence for the emergence of our kind, for the emergence of humans. And it's a fascinating story, but one which represents a relatively small portion of the history of life on our planet. And people like us are only present in the archaeological record for maybe 70,000 years in terms of cognitively modern humans, behaviorally modern humans, maybe a couple 100,000 years for anatomically modern humans. But a great deal of the earlier history is one that is filled with what we refer to as pre-modern humans, pre-sapiens hominins, right? And as you can see here on this chart, it's an important starting point to say we do not descend from chimpanzees or bonobos because we share a common ancestor, but we are not descended from those species that we today know as chimpanzees any more than you are descended from your cousin. You're related, but you're not descended from your cousin. And so that's an important point to make here. We are more closely related to chimpanzees and bonobos than we are to gorillas, and more so to gorillas than to orangutans, more so to orangutans than to gibbons. So the amount of relatedness can be tracked not just with the fossil record now, but with DNA, powerful DNA analysis. Because this class focuses on archaeology rather than the biological anthropology course, which I also recommend you take if this is an area that interests you, we'll be looking at the evidence from the standpoint of skeletal and archaeological materials. And the earliest evidence for our line of primates, the hominins, the bipedal apes, is found in East and South Africa. There have been limited amounts of early hominin materials found from the country of Chad, which is closer to Central Africa, but the large majority of the evidence from many, many different hundreds of sites is found at these places: Ethiopia, Kenya, and Tanzania, as well as in what is today South Africa, are some of the countries that have not only the most appropriate deposits of, as they say, dirt of the right age, but also have had a history of research that has resulted in the discoveries. There may be evidence in other areas that have not yet been investigated, but that is why there's still work to be done in the investigation of the human past. Go out and find it. One of the really, really important areas that has provided some of the evidence for the earliest lines of bipedal apes, hominins, is the Awash Valley in what is today Ethiopia. And you can see here in that draw-out map a couple of other locations, the 5 different locations where evidence for the early human ancestor Ardipithecus have been found, as well as a number of locations where Australopithecine fossils have been found in the same region, though Australopithecine fossils are not limited to the Awash Valley. Speaking of Ardipithecus, those 5 fossil localities have produced over 100 examples of Ardipithecus ramidus remains, and they date consistently to around 4.4 million years ago. And Ardipithecus probably represents the earliest branch toward fully bipedal locomotion. Yes, chimpanzees and gorillas can walk on 2 legs, but it's not their habitual form of locomotion, and they don't do it nearly as well as you do. And that's an important point. The difference between animals that can stand on their hind legs, bears can do this, for example, and animals for whom the bipedal locomotion is the habitual and obligate form of locomotion. Right? You have to move about that way. It's not really modern humans walking on all four hands or all two hands and 2 feet look about as graceful as a bear walking on 2 legs, right? So it's the difference between obligate and optional locomotion. Ardipithecus lived in an open, wooded environment, and they ate a varied diet rather than a specialized one. We can tell a lot of this from their teeth. Not only the shape of the teeth, but the thickness of the enamel influences the kinds of food that animals eat, and is a strong indicator for that. And this is interesting to note because it suggests that the omnivorous diet of our line, not only going back to Ardipithecus apparently, but throughout the history of our species, has been that of an omnivorous primate, not one who was highly specialized to a single form of food or a single kind of diet. We've never been koala bears, for example, just eating eucalyptus leaves, or just grinding up tough nuts and tubers and whatnot. So this is an interesting insight into a great deal of time depth as regards diet. Here on the left is one example of Ardipithecus. This is one from that Middle Awash, one of the Middle Awash localities there. And you can see it's not the entire skeleton, but it's a substantial amount, more than enough to be able to make out significant and important anatomical characteristics. You can see the skull, you can see portions of the vertebral column and the clavicle there. You can see, very importantly, the pelvic girdle, the arms, most of the lower arms, femur, and quite a lot of the lower leg on the right side there. So this gives us a very good view of the proportions of this creature, and you can see a technical reconstruction of the skeleton on the left there, and then an artist's reconstruction of what this individual may have looked like in life. Other species of hominids follow. This is the famous Lucy skeleton, yes, named after the Beatles song Lucy in the Sky with Diamonds, which was playing on the radio when they found this skeleton. Also discovered in Ethiopia in the Afar region. And you can see the amount of this individual that was recovered, as well as the sort of museum-mounted reconstruction on the right there. Lucy was far more advanced in terms of her bipedalism than was the Ardipithecus from about 1 million years earlier. We can see that the greatest area of change in this group of hominins was dramatic increases in the efficiency of walking, the length of the lower limbs, and especially the ratio of the lower limbs to the upper limbs. Proportional to one another, the upper limbs were getting shorter and the lower limbs were getting longer, indicating that these individuals are no longer kind of straddling that divide between an arboreal forested landscape existence and the savanna open woodland places that Lucy lived in, that the Australopithecus afarensis occupied. Of particular fascination is the fact that at Laetoli in Tanzania, a site was discovered by Mary Leakey that dates to around 3.6 million years ago and was dated by potassium-argon dating, where the ratio of radioactive potassium to stable argon in volcanic ash crystals is measured, and that gives you the length of time that ash has been cooled. Located there were over 84 human tracks in volcanic ash. The track weighs about 30 meters long and includes footprints from at least 3 individuals, 2 larger and 1 much smaller, probably a child. Based on the length of the stride, the adults were probably about 1.2 meters in height, or just over 4 feet tall. And you can see here an example where they've done laser tomography scanning of these prints at Laetoli, and then use those to calculate both the distance and angle of the strides. This indicates that by 3.6 million years ago, our ancestors were fully bipedal, as opposed to knuckle walking like modern chimpanzees and gorillas. In fact, it's possible that that kind of locomotion that we see in the modern great apes may have actually developed after the divergence from our shared ancestor. So our ancestors may never have knuckle walked in the same way that modern chimpanzees and gorillas do. The Australopithecine finds in Africa, the Afarensis, like Lucy, Africanus in southern Africa, as well as Chadensis, the one I was mentioning there from the country of Chad, are found across the continent. From Ethiopia to South Africa is where the greatest density of fossils have been recovered. It should be noted, though, that the tropical forest environments of Central and West Africa are not often ideal for the recovery of fossils. It's a lot harder to find fossil deposits in a tropical rainforest than it is in savanna or desert environments where the stratigraphy are exposed and you can walk across the surface of the ground looking for fossils, whereas in the middle of a swamp or a tropical forest environment, even if the fossils are there, they may be exceptionally difficult to recover. However, the amount of mining that has occurred in Central Africa, you might expect that some evidence would come forth. Unfortunately, it's hard to say. That's kind of an open question. Here's the key for looking at these things in terms of understanding bipedalism from the archaeological record and the skeletal evidence. You can see here on the top is the human os coxae, sort of one half of what we refer to as the pelvis, right? And on the right, you've got the examples of Australopithecus and great ape on the right, a gorilla os coxae on the right there, and then a modern human one there on the left. And you can see that the Australopithecus, while not exactly the same form as modern human pelvis, is very much closer. It's a basket, of bone that's kind of holding up your internal organs, as opposed to this long, narrow thing that's a muscle attachment for animals that more habitually walk with their torso leaning forward. Also, some of the differences between modern human pelvis and the Australopithecines is probably attributable, at least in part, to the increase in the width of the pelvis, especially where you see increases in cranial capacity, because a woman has to be able to survive childbirth, as does the infant, and if the pelvis has too narrow of an opening, then that child is not going to have as likely a successful birth. And so as the cranial capacities increased in hominin lineages, you saw some changes in the shape of the pelvis that were not related directly to locomotion, but were related to helping infants and mothers survive childbirth. When you're talking about Australopithecines who had, relative to us, very small cranial capacity, the issue was not a principal one, and so locomotion may have actually been slightly more efficient in some of the later Australopithecines and early Homo than they are in modern Homo, because We sort of gave up some of that locomotion efficiency, the sort of ideal design of the pelvis, in order to be able to accommodate a larger brain. Again, just some more anatomical comparisons, talking about the differences between our forms of locomotion and those of the great apes. And you can see top left there, perfect sort of comparison of these differences in pelvic girdles, and also in terms of the angle of the leg. Anybody who's ever had any knee pain or whatnot can attest to the fact that the human knee is slightly off angle there, and that's to try to bring the balance point from the foot to the pelvis more in line. Whereas because the great apes knuckle walk, they don't have nearly the same structural balance point, which is why when you see chimpanzees and gorillas attempt to walk bipedally, they have that kind of waddling gait from side to side, because the center of gravity is not directly underneath the leg. Also, we have an arch in our foot, which is why we all have to go and get those arch support shoes, because that's another factor relating to the tendons and the muscles and this habitual bipedalism compared to our flat-footed ape cousins. Here you can see another line of evidence where you can tell from the skeletal record something about locomotion and how individuals or how organisms carry themselves. The point at which the spinal column enters the skull. If it's at the rear of the skull, like dogs and cats, then their standard sort of gaze is with their head in line with their spinal column. And they have a really hard time, looking straight up in the air, because that would require, bending the spinal column at 90 degrees, which is generally a bad idea. But with humans and hominins in general, the foramen magnum, the hole in the bottom of the skull, is vertical. That's why you can, take these models that you see, these skeletal models in, anatomy classes and whatnot, and the foramen magnum is just there at the top of the stick. It's a vertical line. It's balanced, so it's like a swivel, right, as opposed to something that's sticking out in front. With great apes, the foramen magnum is further up towards the back of the head, because they don't have a perfectly vertical stance. Also, if you look at the spinal column, there's a significant bend, S-curve, in the portion of our lower back. Again, because the angle between the legs and the spine, when humans are standing and striding and walking, the spine and the legs are almost parallel to one another. Whereas if you think about knuckle walking, the spine and the legs are at an angle, somewhere around 120 degrees. And so they don't have to have nearly that sharp S in the lower spine that we do, which also leads to some of the degenerative issues that we have when those ligaments get a lot more wear and tear on them. I suspect great apes probably don't suffer from lower back pain nearly as much as humans do. So within these lineages of bipedal apes that were occupying a variety of different environments in Africa during this time period, you have their divergence then into a gracile Australopithecine branch and a robust Australopithecine branch. The gracile Australopithecines, there are species like Africanus, Afarensis, Anamensis, going all the way back to Ardipithecus ramidus can probably be the root of that, if you will. But the robust Australopithecines, also known as Paranthropus, sometimes called robust Australopithecines, it's a general category, but the genus today is typically referred to as Paranthropus. are this very specialized line, as opposed to this kind of generalized bipedal ape with diverse diet and not highly specialized teeth that we see with the gracile lines. The robust lineage is one that takes a very specialized approach to food, and all these other factors become secondary to developing and focusing on a particular kind of diet. I'll show you here. So on the left, you can see an example of Paranthropus boisei. This is also referred to as Nutcracker Man. You can see the teeth on this individual are absolutely massive and flat. There's almost no canine development whatsoever at this point, in contrast to the great apes. And the brain case, the chewing muscles you can see here on the robust Australopithecine have been given space by this widely arching zygomatic arch, that cheekbone, right? And you can see on the top of the skull, there's actually a ridge of bone for where the muscles for the jaw attached all the way at the top of the skull. So if you put your own hand, put your own fingers right on your temple and then bite down, right, you'll feel the muscles that are attached there swell. And that's where your chewing muscles are attached, right there around your temple. Boisei's were attached all the way at the top of the head and were so massive and strong, because they go behind your cheekbone, so massive and strong that to accommodate those chewing muscles, they had ever widening arches of these cheekbones to accommodate those muscles. The face, you can see there, has these ridges running vertically down from the cheeks towards the teeth. And this is actually buttressing to strengthen the bone of the face, because the amount of bite force that these guys had relative to the area, if you applied the same bite force in your own mouth, you would not only shatter your own teeth, but probably break your own face with the amount of muscular strength that was just in the chewing muscles on these Paranthropus boisei. They lived in more heavily forested areas rather than the grasslands and savannas occupied by the gracile Australopithecines and early Homo species. But interestingly enough, these robust Australopithecines lived in Africa at the same time as other hominin species, including both Homo habilis and Homo ergaster, the earliest ancestors, the Homo erectus line that were the first hominins to leave Africa, were living in Africa at the same time as these robust Australopithecines. A very, very different line of humans with a very specialized diet and who persisted for a very, very long period of time. They weren't sort of a brief divergence. But it is kind of interesting to reflect on the significance of the fact that the hominin lineage, when specialized, was not as successful. There's no evidence, for example, of robust Australopithecines outside of Africa. So these specialized lineages don't have the same potential as our kind to migrate and adapt and learn new landscapes and do different things, because they have this very specialized biological adaptation that really wouldn't allow them to leave zones where that adaptation was ideal. The gracile Australopithecine line here, represented by Australopithecus sediba, one of the later Australopithecines, again probably overlapping somewhat with the earliest members of our divergent line, where our line splits off from these Australopithecines. From nearly complete skeletons from Malapa Cave in South Africa are too late to be ancestral to our genus Homo, but they are incredibly well preserved, and we have almost every bone. This skull, for example, they've been able to do MRIs on this one and actually recover the shape of the brain inside the brain case. So the preservation for individuals, for examples this old, is really, really remarkable. They were fully bipedal, omnivorous, and there is some evidence that they may have been using some simple tools. But so far, the real marker of what distinguishes our lineage, our divergent lineage, from these other bipedal hominins is our extensive use of technology, our habitual, consistent, and almost obligate use of that extrasomatic adaptation outside the body. We have developed other ways of adaptation rather than Paranthropus boisei adaptation to eating tough foods. We make grinding stones instead of going the biological route here. So it's a different approach to adaptation, and it may be the ability of technology and tools to adjust and adapt so much more quickly than biology that gave our lineage, our divergent lineage, such an advantage over these others. And you can see here, just as kind of a rough example of the human family tree, you can see the Australopithecines, the Ardipithecus group, the Paranthropus group there, and then our group at the apex of the tree. Of course, it does suggest we're putting ourselves at the end point, but nonetheless, it kind of gives you a much more realistic view of what we know about the relatedness between these different kinds of hominins. Here's an example of Homo habilis. This is the Kenya National Museum, East Lake Rudolph, fossil 1805 and 1813 from Kenya, both from Kenya. And you can see already some of the major differences in terms of cranial architecture, the size of the brain case, the dentition, really beginning to approximate something much more recognizably human. And what occurs along with these earliest examples of our genus is the earliest stone tools, dating back to about a little over 2 million years ago. Places where we have seen Homo habilis finds include Kenya and Tanzania, as well as in South Africa. And one of the things that happens after the emergence of our genus is a much more rapid expansion of the range of these early groups. And with the emergence of what's called the erectus line, Homo erectus, you see the first movement of hominins outside of Africa. Now, one of the other things that's really interesting is that you also, with the erectus line, begin to see statures that are closer to the range of variability in modern human populations. The Australopithecines, especially the gracile Australopithecines, little over 4 feet tall. Homo habilis, not quite 5 feet tall. And it's not until the erectus line that you begin to get individuals even close to 5.5, and in a couple of examples, 6 feet tall. Prior to that, the tallest individuals, even among the robust lineages, were maybe 5 feet tall, and that's at the upper end of the range of variability. So you see an increase in stature, you see an increase in brain size, you see an increase in the sophistication of technology, and you also see dramatic increases in the sophistication of the stone tools and the use of meat. You see a lot more evidence for hunting, not just scavenging of remains, which is what we see from the very earliest examples with Homo habilis, evidence for scavenging of predator kills. But with Homo erectus, you see very clear evidence of active hunting and dramatic extension of the range. Instead of just being limited to a small portion of one continent, you begin to see hominins all across the globe. Here you can see Acheulean, which is what it's referred to. The site of Saint-Achille in France was the first place it was identified, but the first place we actually see it in the archaeological record is obviously in Africa. And you see a variety of different forms of these tools, from cleavers to picks, and you can readily recognize that these are not things that are just produced by casually breaking one rock with another. There has to be quite a bit of forethought and planning in their production. There are even some Homo erectus tools from China and East Asia, which is the farthest east that we have evidence for the movement of Homo erectus. They do not appear to have reached the Japanese archipelago, although we do see evidence for Homo erectus in what is today Indonesia, though it was probably connected to the mainland at the time of the arrival. Here you can see those Indonesian examples on the bottom right corner of this map, as well as the Chinese examples of Homo erectus, the ones from the Caucasus at Dmanisi, multiple localities in Europe, including at Boxgrove in England. North Africa has Homo erectus examples, as well as continuing to find large quantities of hominins in East Africa during this time period. And one of the things that's driving a lot of this movement, it is hypothesized, are these cyclical changes in climate. And you can see, especially during the last 2 million years, especially during what's called the Pleistocene or the Ice Age, you see these oscillations back and forth. As you see the global system attempt to reestablish stability after periods of instability, it shifts to either cooler temperatures, glacials, or interglacial periods, warmer. And these shifts, once thought to be gradual, are now definitively known to have happened very rapidly, with punctuated changes in climatic systems, because we now have very high resolution data from a number of different sources that allow us to talk about not only what changes occurred, but at what frequency and with what kind of speed. And so these changes are happening very, very quickly. It's not like glaciers, advance by, a centimeter and then retract by a centimeter. We're beginning to see evidence that, for example, when glaciers began to melt at the end of the last ice age, there would have been time periods as short as a single human lifetime where sea level rose by as much as 15 meters in a single lifetime during the height of the ablation or the melting phases. And so these kinds of shifts in climate and landscape and precipitation and temperature would absolutely have been a factor. Maybe not the only one, but they certainly would have been a factor in causing populations to shift and migrate. And that seems to really be the context in which we see the emergence of our kind, in terms of the emergence of Homo sapiens, really seems to have been in this context of repeated migrations and adaptations to new conditions, not in the context of some kind of ideal circumstance, but rather in the context of having to either move and find a new homeland or change what you do and learn how to do things differently to adapt to the circumstances as they emerge. One or the other, but time periods of crisis and shift and change seem to be the sort of natural state of our people. And these early archaic Homo sapiens, where you begin to see the most modern kinds of anatomical features in these populations, are also found very early on. The earliest examples are from the African continent. What's particularly interesting is that the earliest very anatomically modern people are actually from a site of Jebel Irhoud, which I'll talk about here in a second. One of the most well-known examples of archaic Homo sapiens from Africa is the Kabwe or Broken Hill individual that dates to about 125,000 years ago. Often shown as this very, very robust skull. When you do an actual forensic reconstruction of the individual, they look very human. They look very robust. This looks like a tough gentleman, but recognizably absolutely human. In Europe, they sometimes refer to this sort of range of variation in early humans as Homo heidelbergensis, after a location in Germany. But more commonly, we're beginning to see these as archaic Homo sapiens sites across the old world here. You can see the number of different localities.